comes, the first thing you gotta do is how we model components at the most basic level. We talked about wires, both DC and AC modeling. Then we talked about what the internal inductance was of the wire. I'm gonna put that up there in a second. And I'm gonna talk about it. Let me tell you one thing about this. In this chapter, it's a very broad brush of EMC compatibility, but at least he addresses the primary things you need to realize. And the first thing you need to realize as electrical engineers is when you go to high frequencies, your components are not just resistors, just inductors, and just capacitors. I want you to keep this in mind. The minute you get up around a gigahertz or higher in frequency, all of a sudden the parasitic capacitance on a resistor, the parasitic value of capacitance on an inductor, the actual value of the resistance of an inductor because of skin depth, it becomes a dominant effect. So this becomes very important when you design high-frequency circuits to consider minimizing the size of the components. I can't overstate this. Some of you here will be you'll be designing things that are going to be very high-frequency circuits for 6G. We got 5G now, right? All right? 6G is just around the corner. I expect, and that just means generation. Do you all understand that? It has nothing to do with frequencies. But usually what they want is a higher and higher frequency of operation for one reason. They can get more data through that. All right? There's more, you have a larger data pipe, you can get more information. How many have had communications in here? Remember Dr. Tugnick talking about information theory and the amount of information in any kind of a signal? It's really the entropy. But when you deal with this type of thing, high frequency is important. The thing they don't tell you right off the bat in pure theory classes is building those things requires adjusting your modeling of components to accommodate that. Now I'm going to get to this. Remember, gigahertz is usually the point where all of a sudden things change. And they don't change for the good, I'll tell you that. They change for the bad in a big way. So, first of all, when we talk about resistors, keep this in mind. What I'm putting here, you have to know. You have to know up here, or you have to have an understanding. So when we talk about DC, all right, when we have your standard resistor R, at DC, the standard thing is, this resistor is usually modeled, or I'm going to call it a wire, first of all. Wire. When we talk about a wire, it has W sub R, wire resistance. So if the thing has a length L, it has a radius A, I did this last time, and a conductivity sigma, this is just something that we've done. Then the resistance DC of this is equal, it's proportional to length, inversely proportional to sigma, and then it's the cross-sectional area A. That's just what it is at DC. Do y'all remember that? Now AC, when we talk about this for a wire, still proportional to length, inversely proportional to sigma. If you're talking about resistance of something with constant cross-section, a wire, doesn't matter if it's a rectangular cross-section, circular, elliptical, and whatnot. If it's constant, then this will always work. It's always proportional to the length, inversely proportional to the material's conductivity, and then the area that the current flows through, and that will always be determined by the skin depth. So I'm going to put area here, just A. And if it's a circular wire, A will be equal to 2 pi A, that's the perimeter's length, times the skin depth. How many understand that? All right, if you take the outside rim of a circle, it's 2 pi A in length. It's called a perimeter. If you multiply that by the skin depth, you get this. So this is AC, and I mean, I hate to have to qualify this, but this is when the skin depth is going to be much less than A. In between, you can go ahead and write the formula, the exact formula for A, and I might as well put down A exact is just going to be pi times A squared minus A minus the skin depth squared. But here, the skin depth still has to be greater, or I mean less than A. Y'all follow me on that, class? This one will work, but you're almost never going to have to do that. All right, I'm just counting that. Yes?
So that's for when the skin depth is not much less than A, it's just like less than?
This is the exact one, if it's less than A.
Okay.
Right? And I don't really try to focus on points that I'm not going to I don't consider that important, but I just want you to understand that. That's the catch-all. And so that's constant cross-section. This is, it's circular cross-section. If it is a rectangular cross-section like so, where we have a width W and a height H, then just think about this. If we have this condition right here, if the skin depth is much less than A, or then in this case, it wouldn't be A here, it would be W or H. In other words, it's something small compared to the geometric dimensions. Then you just go around the perimeter here. Can you all imagine this here? And that would be the area the current flows through. You all see that, class? Can you see it? Back here? Not far back. Can you see it in the back there or not? Very back? Okay. Because you're looking through 3 heads, and I don't know how you do that. But okay. So this area here for this one would be equal to, it's just the perimeter, right? So it's 2W, right, times the skin depth, plus then 2H times the skin depth. Y'all with me? And by the way, skin depth is always going to be equal to 1 over the square root of pi f mu sigma. You need to know that too. You use that all the time. Everybody with me on this, class? I mean, you understand the principle. You go around the rim of anything, make it 1 skin depth deep. That's the area the current flows. It doesn't flow in the center. Which is why you'll see so many high frequency things, when they have connectors, have absolutely hollow centers. Has anybody observed this? Anybody work around microwave? You have? When I did my PhD work, my master's work, it was with plasma etching materials. And I noticed when I got in there, it's a 2,000 watt system, all the piping was hollow. It's only at 13.56 megahertz, but they realized putting metal in the center is a waste of time because the signal never gets there. It's a waste of metal, it increases weight, cost, everything. So you will see high frequency stuff, conductors that just have, they're hollow. Or they have just something in there in the center to support it or pull it. Yeah.
That's basically a waveguide, isn't it?
Well, no. Waveguide, remember, you have signals bouncing around. All right, but there is a circular waveguide, all right, without no interconductor. But the way this has a constant potential where the currents are driven down the axis, there's no fields inside to speak. I just want to make sure. Oh, it's not a waveguide, but I can understand how you think that way. It could be used for. Okay, so that's that. Now, remember we talked about, what about the inductance? That's for a wire. For a wire, we talk about internal, and underscore that. This is inside the wire. Internal inductance. All right, now, internal, so a wire is basically something like this that has a radius A, conductivity sigma that doesn't do anything for inductance, remember that. And it has some permittivity or permeability mu. Y'all with me? All right, so when we talk about inductance, there's a DC inductance, and this is usually per length. So I'm going to leave this one as per length. This is per unit length. And that's just mu over 8 pi. And that's henries per meter. How many remember me talking about that last time? What was the one thing I really wanted you to see and notice? There's one critical factor. It doesn't matter what the radius is. Do y'all see that? It doesn't matter if the radius of the wire is 3 meters or 3 centimeters or 3 millimeters. That is the amount of internal inductance. It's because the current uniformly spreads out over the cross-section of DC, and the energy density will be such that no matter what you do, that will be the internal inductance. How many of you know what the energy is that's stored by an inductor with a current I? Raise your hands. This is a catch. This is one of these things, when you go for an interview, and they say you're an electrical and computer engineer, this is one of the things they may ask. They have a bunch of what they call it's weed out questions. If you don't answer at least half of them right, you're not an engineer. You're something, but you're not an engineer. Not in their mind. All right, so if you have an inductor, just for the record, L, all right? The energy in this W sub E is usually the way they denote energy. This is the energy, is 1/2 Li squared, all right? That's the energy in an inductor. How many remember it now? All right. Now, there's something else you should remember while I'm on this. If that's a capacitor, right, and there's a voltage across that capacitor, how many know the energy in the capacitor is 1/2 CV squared? Remember that? All right, it's important you do, because that capacitive energy, the ability to store energy for a given voltage, all that energy is available to, you can pull it out. With this current right here that's flowing through there, you can reroute that current through a resistor or an antenna, and all that energy is available to dissipate or propagate, either dissipate through the resistor or propagate from the radiation resistance. Y'all hear me on this, guys? So that's the reason you keep that in mind. Now, these supercapacitors that they have, that can store a fair amount of energy. The real thing is that you can short these things. Like when you start your car, you need a lot of current, right? Well, if you had a capacitor that had only a 12-volt breakdown strength, roughly, a little more than that, and you charged it so it had maybe 10 times the charge you would need to sustain 100 amps for like a couple of milliseconds, you all see where I'm going with this? Then starting your car when it's really cold because your battery, your lead acid battery can't crank would be a benefit. That's what they're doing now. How many know this? All right. How many know that most cars, the modern cars today, not all, they have what are called energy scavenging brake systems, or they have brake systems that charge batteries? How many know that? Like hybrid vehicles and stuff? All right. That's where things are going, and really you have to be aware of energy always. You have to be aware of that whenever you're dealing with these kind of systems. Just remember that. Okay, so that's the DC inductance, but it's only internal. Do you remember what I talked about AC inductance, when all of a sudden the skin depth is much less than A? There's the L, and I call it AC, but it could be high frequency. Sometimes they'll put inductance high frequency, and this will be per unit as well. Anybody remember? What I like to do, Wentworth does it, take the DC per meter. So just put LDC. That's that one. You could put it down. And then you simply put 2 skin depth over the radius A. Now, anybody looked that up in his book? No? It's there. I gave you the equation last time. Look it up. All right? I know you had a quiz, but just look it up. And it's in there. It's different than the one I showed you. I like just putting LDC because that's right there. Times that. Wentworth does it. He puts this here, and then he gets rid of the 2. So it's mu over 4 pi A, and the skin depth's on top. Y'all follow me? That's what's in his book. Yeah.
Yesterday you had something that's like LHF that equal that same thing.
High frequency. HF, AC is, you know, you could put L, high frequency. These are just different things that denote the same thing, because AC means it's time varying current, but the real critical factor is the skin depth, regardless of the frequency. If skin depth is less than A, default to this. Okay, but this is just internal. You all hear me? Now, something he doesn't get into in the book, wouldn't you think most of the energy in the magnetic field is outside the wire? Doesn't that at least make intuitive sense? Well, it is. But they can't talk about a general formula. He has one called partial inductance, and here's why. Because the only way you'll find out the amount of energy associated with a given current element is know how the return current gets back to the source, all right? So if you have 2 wires that are separated by nanometers, all the energy is internal to the wires because there's no real area for the fields to expand. You all follow me? The fields are basically 0 outside of those 2 conductors because they're almost on top of each other. If you have a coaxial cable, you have an inner conductor and an outer conductor, where the outer conductor's current is exactly equal to, but in the opposite direction, there is no magnetic field theoretically outside there. It's all contained within. Then the internal inductance of your core is pretty much the internal inductance there and the energy inside it. That's it. But if you have 2 wires, now think about this. You're used to seeing extension cords and stuff, right? What if I have a wire like this that goes down to the back wall, comes up and goes this way here? Now I have this giant cross-sectional area where the actual magnetic flux will go, and there will be a large amount of energy outside that circuit. Do y'all follow me? I learned a hard lesson in this with railguns one time. And it had to do with cabling hanging all over the place when we did discharges, up to 400 kiloamps, by the way. I learned there was a ton of energy in the air, for starters, to cause electrical shocks. I literally saw arcs out of that wall down to the ground happening because of this. And I'm not going to get into all the physics that are happening. The other thing is, you know, if you have current and there's a magnetic field, there's IDL cross B as a force, right? Well, and boy, was there a force. The thing was like a whip, all right? We found that out the hard way. We didn't, it didn't dawn on us how much force would be generated. And these kids, of course, used this in their best interest. We had a large inductor we had to create specifically to slow down the discharge of these capacitors so we could fire this gun. And I can't get into it all. If you put it instantly, all right, then basically you got a firecracker and nothing goes down the barrel. All right, but you want a continual force as this thing's going down the barrel of a railgun. I won't get into it now, but I will later. All right, so I'll try. So we needed this inductor, and they used hollow PVC with large 4-aught cable that they wound, and they used Bondo to hold it down. Y'all know what I'm talking about? Fiberglass, that stuff you fix your cars with, and boats. All right, well, then somebody thought, hey, that's an enormous magnetic field in the center there. And that would induce a current on a conducting can. They liked Southern. So they emptied a couple of cans and they threw them in there, and we fired the inductor, unbeknownst to me. And it was basically a mortar, boom, into the ceiling. And I could see where this is going. These kids wanted something that would kill me. They were getting there in a heartbeat. I'm not kidding about this. They had more fun. If you ever talk to anybody that's ever did that project, they're 20 years back, they'll tell you stories that I probably will never know about unless you tell me, because they don't want me to. The stuff that they did with that gun. Anyway, that's no longer here because of 9/11. The Homeland Security Department figured out that other groups were interested in it besides my so it's locked up in the security person's office. Okay, so back to this stuff. Now, here's the deal with inductance outside the actual wire. So when you have an external inductance and you just want to estimate, there's a lot of ways to do this. I will give you this formula if I expect to use it. If on page 505, he talks about the partial inductance formula. This is only one of many. So if you have a wire and you basically want to estimate without knowing the return path, and this is L, what the external inductance is. This is L external. All right. And this isn't per unit length. It's 2 times 10 to the minus 7th in the henries per meter times the length L. And maybe I should use the script L he does here, because this could, L usually means inductance, times script L here. And then it's times, this is the natural log, or log base E, of 2L over A, I got a comment about this, minus 1. And this is in henries per meter. Now, if you look over here, at this one, you see this term 2 skin depth over A. Yeah, this is 2L over A right here. It's similar but different, but I want you to notice one thing here. If this right here is 1, this is negative. Do you all see this, class? All right, so there's a requirement. L has to be much, and make it much greater than A. If it isn't much, longer than the radius, you can't use this formula. Y'all follow me? Like 100 to 200 times. Now I got to tell you something else about this. You'll notice how there's nothing said in here about the return path. Right? So this partial inductance they justify by making assumptions about the return path. One is it's in proximity. But I'm going to tell you, this is just one of many formulas. The only way you get the real inductance, external inductance, in a wire is by knowing the entire path the current takes and then modeling it. You can do simulations to get that, all right? But I'm gonna tell you, it's not easy. Most of the time, they have good ways to estimate. Y'all know that the standard lines you get, like extension cords, have two conductors separated by a constant distance. Y'all follow me on that? That inductance, external and internal, is very well known. When you have two conductors that weave, you know what Cat5 cable is and stuff? They have what are called, they are something where they have a whole bunch of conductors that are woven in a way that minimizes the actual electromagnetic interference or the actual interference of one wire on another. And I can't get into that now. Just realize there are a lot of common ways that conductors are laid out, and they're easy. Those inductances, external and internal, are well known. I just wanted to put that up. Okay, so that's basically internal inductance, internal resistance for both high frequency and DC, and this is external inductance. So now for a wire, we've basically checked the boxes. If it's high frequency or low frequency, how to get the inductance. External and internal. Y'all follow me? Next thing we do is the components. And the first component is a resistor. Now, you're used to seeing resistors as what? About carbon resistors, maybe a quarter to maybe a half-inch long, and they have a color code on them. They're cylinders, right? Those are carbon resistors. You'll find in the real world, resistors take every shape in the world. They can be serpentine. A lot of things are conformally mounted on things. Resistance isn't the big deal usually, but there are times you need a critical value of resistance for certain balancing, things like this. However, you have to have an electrical model of resistors that accommodates the high frequency effects. And I don't know, you know, I'm not really sure, what's the highest frequency lab you've done so far? Anybody?
Signals and systems?
Have you done a gigahertz lab or not? Anything over 10 to the 9th hertz? Megahertz? What was radio lab at? Kilohertz, hundreds of kilohertz or megahertz? That's very low frequency. Nowadays, your Wi-Fi routers are 2.45 gig, right? I mean, isn't that standard for most still? You've got a couple of different frequencies.
They're pushing out 5 now.
5 gig, it's low gigahertz, right? In the real world, you're going to be dealing with 80 gig signals. Car radars now, the standard car radars are 77 gigahertz. At that frequency, everything changes for your standard ideas. So, when we talk about a resistor and we're doing high frequency modeling, regardless of how it's created, you always start with what the resistor looks like. That's it. That's the resistance that you would read off the barcode. Now, after that resistance, you ask yourself this. If current comes in here, there's necessarily a voltage V across it, right? Anytime you have a difference in potential, you have electric field lines like this. You don't know how they map, but you'll have E field lines that'll basically be doing this, and you know that, right? Because you effectively have two charge centers. The only way you get a plus to minus charge, if it's not an induced EMF, is by having some delta Q difference, right? Anytime you think about a voltage difference between 2 points, think about a capacitance. That means there's an effective parasitic capacitance, C parasitic, between those 2 points. I'm going to model this in a second. Does that make sense to everybody? It's just a reality. You can't get away from it. Now here's the next part, is dependent on the way the resistor is built. And anytime you have a resistor, you have a voltage. By the way, Dr. Wentworth's book on page 508, he shows you a serpentine flat resistor that's conformal right on the top on figure 9.6. I'm going to show, there's a lot of different methods for doing this. It has to do with the specific resistor. But I'm going to just tell you that that could be a resistor or an inductor, actually. I think it's a resistor in his case. That most resistors like this, they're made that you have wire, you have a resistor, so you're going to have this parasitic capacitance. What else? If you have wire and you have current, what do you always think of as one thing that's inevitable? Well, yes, but that's inclusive in the statement on the resistance, right? But there's, what about, anytime you have current, you have, I erased it,
Inductance.
magnetic energy and inductance, all right? So the most common way to draw the equivalent high-frequency circuit for most resistors, unless there's something very odd about the shape, and this is just standard, and this is the one you'll be responsible for, is this. Always start with the element itself. That's what it'll look like at low frequencies. Now, anything I put in there can't alter the way it looks at low frequencies. Keep that in mind. Now I'm going to put a small capacitor here, and that's parasitic. That's what that sub P means. It's unwanted, but it's inevitable. And then, because mainly the length of these wires, keep this in mind, the length of the leads is critical. You get an inductance like this. L, and call it L lead. Now in Whitworth's book, he'll talk about, well, there could be an inductance internal there. But usually that's so insignificant, it's not worth talking about, if there's any proper design. Mainly it's the leads. Have you been told when you built circuits and stuff to cut the leads as small as possible before you solder them? Remember that, and I mean, if you ever have to do any high frequency design, especially your first time, if you're building anything for a radar circuit, anything like that, where it's over a gigahertz, get your lead lengths as small as possible. And one other thing, apply the least amount of solder necessary. I think I told you a story about my antenna going south because of a solder hole. That always sticks with me. That was a lot of money, and I could have been out a lot of money. So I appreciate the fact that soldering is important, done by whoever. And this is what that circuit looks like. So when you look at that right there, that's a fairly easy thing to model, isn't it? I mean, do you all agree with that? Now look at it. At DC, what does it look like? What does an inductor look like DC?
Short.
Short. What does a capacitor look like at DC? Open. It's a resistor, right? It better check that box. It should look like what it should look like at low frequencies. All right, so how do we model this? There's a couple of ways. We know what the impedance of this is really 1 over SC, and the impedance of this is just S times L, isn't it, class? Y'all with me? Are you familiar with SL? I mean, S is J omega, okay? All right, if you think about that, what is the impedance of that? Well, it would be SL, right? Plus, these two are in parallel, right? So I can have 1 over R plus SC. Y'all agree with that? I'm just showing you the way I would do it. Right? 1 over the resistance, plus 1 over the impedance of the capacitor is 1 over SC is the impedance, 1 over that is SC. Y'all follow me on that, how I got it? All right, now I'm just going to modify it slightly. This is equal to SL plus, and if I multiply top and bottom by R, I get R over 1 plus S times RC. Sometimes you'll see this replaced by tau. All right, RC is usually tau, it's a time constant. And it looks like that. Now you can keep on going, and you can get a common denominator, so it depends on how far along the line you want to go on this. But this is the way it's plotted. Do y'all follow me what I'm doing here? Now we can break this down. I can multiply that times that if you want. You don't need to do this, I'm just going to show you. You can get SL times 1 plus S times RC here, and then you have 1 plus SRC here, and then I can multiply through by SL, and I can fuss with that thing, but I'm going to tell you what happens. What they really do most of the time, if this is the impedance Z, right here.
Are you missing R, or am I just?
That's RC right here. Oh, you know what? You are absolutely
Just
right.
plus R, right?
Plus R. Thank you very much. I'm going through this kind of casually because I don't want to waste too much time right here. You're going to do this for probably one of the homeworks you're going to mess with this, but I'm just going to show you what happens. The way they plot these things isn't a linear plot. What they normally do when they do this is something called a Bode plot that you've heard about. And for Bode plots, what they do 99% of the time, that's going to be 20 times the log of the magnitude of the impedance on that axis. They let S become J omega, and on this axis here, they're going to plot either omega or they're going to plot F, either one, and it won't matter because it's logarithmic, all right? Now, y'all remember this? You remember Bode plots? All right. So when they do that, you're going to get this for a resistor every single time if that's the model. Please write this down. It's in his book, but it's kind of something you gotta read it carefully to discern. In the beginning, at low frequencies, you can call that 0, but remember, this is going to be, this scale here, I'm putting omega, it's actually the log of omega. You're actually going to be this scale. So you're going to get something where there'll be a starting point, and each one of these will be that logarithmic. Like this could be 10, 100, 1,000, 10. Y'all follow me on that? So this is a log scale there. That's that. And here's what happened with resistance. You start off, and this line will just be 20 times the log of the magnitude of R. So it's going to be, if you have an R of 10, right, the log of 10 is 1, it would be 20. All right? But we know that's 20 times the log of R. It's going to stay there until it hits this point right here. And this point, I'll tell you what, let's not do it with omega, let's do it with F, because it'll be easier to you to remember. So I'll let S equal J omega and omega equal 2 pi F, or S, go to J times 2 pi F, right here. And we're going to plot it versus log F, because this is the way I think he does it in his book. Y'all follow me what I'm doing here? There's going to come the first frequency, I call it FL here, and FL is the low frequency cut frequency, and that's equal to 1 over 2 pi R times C. So this would be the first pole, and it'll start coming down right here at 20 dB per decade. I'll go over this a little more in detail in a second. Y'all follow me on that? Now this is the one that's really critical. It's called the self-resonant frequency. Put a line here and put FSR, it's self-resonant. This is the frequency where the inductor and capacitor resonate. It will be the minimum possible value of the impedance of that circuit right there that represents a single resistor. The F self-resonant is going to be equal to 1 over 2 pi square root of L, and this is the the lead L, I'll just put L so lead, times C parasitic. Now y'all remember the self-resonant frequency for an inductor and capacitor was 1 over square root of 2 pi LC, or 1 over 2 pi square root LC? How many remember that? All right, or omega, the omega resonance was simply 1 over the square root of LC, right? Do y'all remember that class? This is critical as electrical and computer engineers for you to know. Now, that frequency is the one, that determines so much. That tells you sort of a limit you don't want to even get close to. Whatever the self-resonant frequency is, based on modeling. Remember how we well, I'll get to that in a second. You know how to do it for a wire, right? But I've got to talk about resistors, how to do this later. Most of the time, the parasitic capacitance and the lead length will determine the actual inductance, self-inductance. Most of the time, they're available from these, the information you get when you buy the component. Have y'all bought components and had like data charts with them, capacitors or anything, chips? They'll show the frequency response, S parameters. They'll show you the information you need to engineer with that thing, whatever it is. Now keep in mind those data sheets, the specs on those, you have to always be careful of units. I'm going to level with you. You're going to see sometimes they'll put units on there that you're not familiar with. I really mean this too. Instead of frequency in hertz, I'm just used to seeing frequency in hertz. It'll be an assumed frequency in radians per second, and that's I'm telling you this now, you've got to read through the data because it has to do with the manufacturer created it for a very specific group of people. If that's what they use, that's what they get, so keep that in mind. Anyway, that's self-resonance. Now after that, the thing starts going up at plus 20 dB per decade. Now, back to this thing here. You notice I didn't multiply the whole thing through yet, right? But I want you to notice something. This is real important. Actually, in Whitmore's book, he shows this at the bottom of page 509, but it's not a Bode plot, it's the actual measurement, but he's plotting it with logarithmic horizontal axis and a logarithmic vertical axis. How many have the books here? You do? Anybody else? You see it? It's on page 509. Most of the time they do these with Bodes. They're straight line approximations. And this is real important. Now, when you do this, just look for a second. Up top, I have the highest power on S is S squared. You all see that right there? All right. Downstairs, the highest power on S is just singular, it's 1, right? So S squared over S is just S. In the limit for high frequency, it should go up as S, or it should go up proportional to frequency of 20 dB per decade. You see how it does that? That checks that box. At low frequencies, we know already it should look like a resistor, and it does. This between here and here is where the critical drop occurs, you might say. And the rule of thumb, he has something about this in his book. I'm going to level with you. I'm not absolutely certain this is true in every case, but usually you want the self-resonance frequency to be 10 times higher than the highest frequency you'd be concerned about. You don't want to be close to it. Factor of 10 is usually a good standard way to keep away from things. Because the minute you start getting close to this, all of a sudden, the value of the impedance that you were expecting there, like, it could be anywhere on this line, and you don't want that. Now, if you think about this, if you think about a factor of 10, that's 1 solid decade. It's very rare for this thing to be separated by more than a decade and a half at best, okay? So I'm just telling you that. That's the standard thing. Okay. I'll have you prove that in your homework that you'll get extra credit for. I'm not going to ask that on a quiz because I know what I'll get. Anyway.
Dang.
That's it for resistance. Y'all follow me on that? Key points, cut off, right down the first break frequency due to the resistance and the capacitance pairs and the self-resonance. Those are the things. That's the resistance. We'll get to how we determine some of these values in a second. Next is a I'll do a capacitor next, because that's the most common thing that causes problems. It really fouls up high frequency operation. How many of you have designed op-amp circuits, done circuits, or done anything with op-amps? Measurement? Didn't everybody in here have? You've been exposed to operational amplifiers, right? Did you ever use an inductor in an operational amplifier circuit? You never do. You don't need to. You know why you probably don't? I mean, there's a lot of reasons, besides I hate inductors. The real reason is for VLSI technology, large-scale integration, you don't want to build an inductor. It's easy to build a capacitor, it's easy to build a resistor. Inductors are an absolute pain in the butt at VLSI because they require a lot of area and stuff. There's other reasons for it, but I'm just telling you, you don't want inductors. All right? If you absolutely have to have one for some stupid reason, then what you do is you usually insert one topically in a circuit later. You don't want, you know what VLSI is, right? That's masking, lithography, all that. How many have had that? You've had microelectronics. No? You all had microelectronics. Didn't you have how silicon transistors are created with? They put down a photoresist, then they develop on top of a layer of the silicon. They get rid of that exposed area, and then they, usually a high temperature dopant is driven in, right, for the base. Then they strip that mask off, right? They do an anneal, and then they put another mask on, expose it, and then they put the emitter on. Do y'all remember this? Then when they do that, there's progressively higher doping levels, and they're either P or N type, right? Well, that's called VLSI technology, and you can make 30 million transistors in something that big topically. Right? I mean, that's a bit of an exaggeration, but you can make a whole lot. All right? What you don't make a whole lot of is inductors. So keep that in mind. You can make capacitors, you can make resistors, but inductors are an absolute pain. And transistors. Okay, next, capacitor. So, what do the capacitors look like that you're used to? This is the symbol we use, right? So at low frequency, it better look like that, right? It better look like that. Now here's the thing, what do capacitors usually look like? They're small, right? They're form-fitting. They could be barrels. You all know what electrolytic capacitors are? You all know what I'm talking about?
Yeah, cams.
Why? I mean, what's the thing with electrolytic that you got to keep in mind? And this is an important point.
Polarity.
That's right. You can't drive current into them the opposite way. They're only polarized in one direction. They have a gooey dielectric that's polarized, and they're lossy usually. They usually have a fair amount of loss. Keep that in mind. They're usually cylinders, if you've ever seen them. They store a lot of energy in a small, volumetric footprint. But you can't put current into them the wrong way. And they go bad fairly often. I don't know if you know that or not, but they do. Second type are things made with standard dielectrics like mica and things like this. These are these little, a lot of times you'll see discs, these small discs that have 200 picofarad on them. Rarely do you get them over 2 or 3 microfarad unless they're very low voltage. You all know what I mean? Now those capacitors are kind of interesting the way they're made. But the way you build a capacitor has a lot to do with the modeling. Has anybody ever built a capacitor? You probably haven't, don't know. A standard, did you have, in physics, did you have a lab where you put aluminum foil down, then you put wax paper on top of it, slightly smaller in form, and then you put another layer of aluminum foil on that slightly smaller footprint, and you rolled the thing up? And what you had is 2 pieces of metal separated by a piece of wax paper, and you could put a charge on it. Couldn't put much because it would punch through the wax paper if you had too high a voltage. But you could discharge it, and you could actually estimate the capacitance in that by epsilon A over D, where D would be the thickness. Do y'all remember that? Anybody ever do that? That's all right. They gotta take care of certain matters. You got the stuff with the pendulum swinging. Didn't you get that? Did you get anything where you fire something and estimate how far it goes? Okay. All right. You got the standard kinematics, but the other things are kind of cool too. Anyway, that's a capacitor. You roll it up. So now the dielectric is wound. All right? But dielectrics can be stacked. Y'all follow me? When I say wound, is you got 2 sheets and then you wind it up into a Tootsie Roll kind of shape. Like this. All right? That's what I'm talking about. And then you make the connections to the inner and outer. But all these things are just, I'm telling you this to give you some sense of what I'm talking about. But with capacitors, modeling them has a lot to do with the way they're made. The standard way for most disk and low loss capacitors, this is not true for electrolytics, is this way. You start with the capacitance. Now, anytime I have current and I have a wire, I have inherent resistance based on that wire. So then you put a resistance like this. And that's, or you can call it parasitic, it's unwanted. And then you're going to also have L lead. All right? And that's what this looks like. This is 1 over SC, this is just RP, and this is SL. And you can find that the input impedance of this will just be 1 over CS plus RP plus SL EAD. And I can go through this, and I will, but I want to make one point. What happens to this thing as S goes to 0, as the frequency goes to 0? What happens to the impedance? Goes to infinity like it should, right? So the model we have makes sure that at low frequencies it checks that box, it works. What does this actually look like? In his book, let me show you where he's got this. Give me 1 second. He's got this on 515. He shows it. But here's how this works. when you talk about capacitive reactance, again, you're gonna have 20 times the log of the magnitude of the impedance of the capacitor here, versus, and this will be logarithm of frequency. This is a nice one to remember. You only care about one thing. It's coming in at infinity. You all agree as S goes to 0, this thing's going to infinity. Log of infinity is still infinite. So it's coming in at a rate of minus 20 dB per decade, and depends where this low frequency is. You can never plot absolute 0 here. So you're going to start at like maybe 10 hertz, 100 hertz, something like this. But here's the thing. The self-resonance right here, F self-resonance is the only thing you need to know. And that's 1 over 2 pi square root of L, and that's L parasitic, or L lead, it's unwanted, times C parasitic, or actually C period, it is the C. And so the self-resonant frequency is the only thing you care about. And then it starts going up to 20 dB per decade. Now, I don't have time for this, but in his book, he talks about the inductor model. Inductors, they can be modeled all sorts of ways, but I just want to tell you his plot of the way an inductor looks on page, the bottom of page 511 is correct. So he has an inductor, the actual inductor. Then he has the resistance associated. This is R parasitic or R unwanted. And then he has a capacitance across here. It's a parasitic capacitance. And this would be Z in of the inductor. Now this is the actual inductor. But remember, if you have an inductor, you have a time-varying voltage through it, you have time-varying current, you have a time-varying voltage, and it's just like the resistor. You have to have a capacitor to accommodate that. Now inductors have a lot of turns most of the time. Y'all know that? Most inductors. Well, when you think about that, each one of those turns has a small but measurable resistance that does change with frequency. Remember, as the frequency goes up, the skin effects make this go up. So this is the standard model. Here's the caveat with this. This resistance is very sensitive to the frequency, so the gauge of the wire becomes important, you know. I don't really test you deeply on this. This particular model will look like this. If you plot the log of F, and this is the way it's always done, versus 20 times the log, or the logarithmic impedance Zn, we could get into this, but it does this. An inductor is basically coming in, down here, it's going to be just 20 times the log of that R at very low frequency. You don't even worry about that R usually, and it does this. Here's what you're worried about is the self-resonance. And that's equal to 1 over 2 pi square root of LC, and this is L lead times or L itself, the actual value of L times C parasitic. And this is shown. And this is going to be minus 20 dB per decade, and this is plus 20 dB per decade. Y'all with me on that? Now those are the 3 plots I wanted to get up there. You can do the math on that and show it. What I'm going to do is probably give you some homework on this just to make sure you do the plot, and I'll probably give you some extra credit for it. I'm not real happy about certain things, but I'm in a good mood. Look, I'm surviving. Everybody else. Yeah. Did you have a question?
Is that 20 log of Zn?
See this input impedance right here?
Yeah.
It's the equivalent high frequency impedance of the inductor. I didn't have time to start with the inductor. That's what it looks like at low frequency, but yeah.
Should we expect a quiz on this on Friday?
I'll let you know. I'm thinking about it.
Okay.
I'm actually, you know, the thing about it is we didn't have time to really dive into this.
Attendance quiz.
Yeah, we've been waiting on that.
You really, it's like, I'll try anything, sure. No, I might give you a sum to turn in for extra credit though. I'm trying to do my job here, make sure I hold you accountable for whatever you get credit for. You never give people just free points. Okay, 5 points, sure. I like it.